In this section, we're looking at angle bisectors. And with angle bisectors, we start with our angle bisector theorem. And that says if a point is on the bisector of an angle, then it is equidistant from the sides. So what does that mean? So let's start with our angle here. I'm going to say this is angle A, B, C. And we're going to put D here as well. We'll go point D right there. So if the point is on the angle bisector, there we go, then it is equidistant from the sides of the angle. So let's kind of take this apart and look at this in congruent triangles like we've done previously. So if I knew these were congruent and I know it's equidistant to the sides, I can draw this out. And suddenly this looks a lot like congruent triangle problem. I'll even draw it over here and kind of look what we have. Now, we have a reflexive side, so that's going to help us, but we kind of need something else. Our goal is to show that these two sides are congruent, so we can't use that as a reason. There's something else we can add here. Whenever you talk about something being a distance from a point to a side, we add in a right angle, so we make it perpendicular. So if I'm measuring the distance from this point to this side, that implies it's going to be a right angle. It's kind of like when you measure your height, the point to the top of your head to the ground, you measure perpendicular to the ground to measure how tall something is. We don't like measure off to the side and get some random measurement, so we want that perpendicular. So that's why we're also going to put right angles there. That's something that we just have implied whenever we measure. So with that, we can look over here, and in congruent triangles, it's an angle-angle-side congruence, which then, if it's angle-angle-side, the two triangles are congruent, and then you can get to these two parts being congruent. So let's phrase this in terms of the diagram I have. So if BD bisects angle ABC, then we're going to say that AD is congruent to DC. And we're going to add a little note here that the triangles are congruent by angle-angle-side, and AD is congruent to DC by CPCTC, where corresponding parts of congruent triangles are congruent. Now, the next one, we take the converse of the angle bisector theorem. So if a point is on the interior of an angle, so we're going to put D here, A, B, and C again, and equidistant from the sides of the angle, so right there. So I put a point somewhere inside the angle. It is equidistant to the sides, which also means we get right angles there. Then it lies on the bisector of the angle. Or lies on the angle bisector. So we can draw this out from there. So let's go over here and draw out and look at congruent triangles, how this works. So we know that these are congruent. We have right angles. If we split it into two triangles, these two triangles are now congruent, not by angle side side, because that still doesn't work, but HL. So because of HL, we get two congruent triangles, which then tells us that these two parts are congruent because those two parts being congruent gives you an angle bisector. So let's phrase it over here. If AD is congruent to CD, and of course that means that AB is perpendicular to AD, and BC is perpendicular to CD, because that's what we get from the distance, then we know that the angle ABD is congruent to angle CBD, which makes it an angle bisector. What we used here is we used HL to get congruent triangles and CPCTC to get the angles to be congruent. Now, we're going to have problems where we deal with just an angle bisector on a single angle and we solve problems. So looking down, that's what those are. But what we also get is one of our points of concurrency, which we call an incenter. So the point of concurrency, or the intersection of the angle bisectors for the angles of a triangle. So these three angle bisectors meet at that point. So when we look at the diagram, P is the point that all of the angle bisectors meet at. We call that the incenter. And from the angle bisectors, they meet at this point. This then lets us say that this point is equidistant to all of the sides of the triangle. And again, as we measure that distance, we have the right angles again. So the incenter is equidistant from the sides of the triangle. One way we can remember that is the angle bisectors come from the vertices, or the angles. They go to the center, and then they're the same distance to the sides. Now that same distance also means we could put a circle on the inside of that triangle with P as the center, and that circle would be inscribed like an incenter, inside the circle hitting all the sides at one point, because we know that distance would represent their radius. So let's kind of look at our angle bisector problems for solving. So I need to find the length of PQ. I've noticed here that SQ is the bisector of the angle, but we can also think of this as like having two congruent triangles and we are matching corresponding parts. So if we had congruent triangles, it would be angle, angle, side, and CP, CTC allows us to solve for it. But in this case, we're just going to say that PQ is equal to QR, and say that 8x minus 27 equals 4x plus 33. We subtract 4x to the other side, we get 4x minus 27 equals 33. We add 27 to the other side and we get 4x equals 60. And we then arrive to x being 15. That is not what it's asking for though. It wants PQ. So we're going to substitute back into PQ, which is 8x minus 27, or 8 times 15 minus 27, and we get 120 minus 27, which gives us 93 units for PQ. For the next problem, we have the measure of angle BDC. So this one is saying if I had this angle, this point is equidistant. Again, we have triangle congruence of HL and CPCTC to allow us to solve. We're going to set these two angles equal to each other. So we're going to say the measure of angle ADB is equal to the measure of angle CDB, which is 9x plus 5 equals 12x minus 19. We then subtract 9x from both sides and we get 3x minus 19 equals 5. Adding 19 over, we get 3x equals 24, and we arrive to x equal to 8. We have to be careful, what are we looking for here? We're looking for BDC, which is this angle. So I could substitute 8 back in to 12x minus 19. So that gives us the measure of angle BDC is 12 times 8 minus 19, which is 96 minus 19, or 77 degrees. So the 77 degrees would also be this angle if we were asked for it, or we could go further and find other values, but that's what we're looking for here. Next page, we have a similar problem as we just looked at, but now we're going to look for WYX, or the total between the two angles. But we're still going to go through the same process of setting both angles equal to each other and solving. So 9x minus 28 equals 5x minus 8. I subtract 5x to the left side and I get 4x minus 28 equals negative 8. I'm going to add 28 to the other side and I get 20. So 4x equals 20 gets us to x equals 5. Now what I can do is substitute this in to find what values I get. 5 times 5 is 25, minus 8 is 17. 9 times 5 is 45, minus 28 is also 17. And those should be the same value because those angles are equal. But what we need is the measure of angle YWX, which is the entire, or the two angles that we have here. So that's just going to be 17 plus 17, or 17 times 2, which is 34 degrees. For our next one, we need to find the length of ML. ML is matching to KM, so we can set them equal because we have an angle bisector. So LM, or ML, is equal to KM. So 5x minus 4 equals 2x plus 5. We're going to subtract 2x to the left side, and I get 3x minus 4 equals 5. Add 4 over, we get 3x equals 9, and x equals 3. Since we're looking for ML, we're going to substitute this in. 5 times 3 minus 4 gives you 15 minus 4, or 11, for ML. Moving down, we have angle ADC has an angle bisector of DB, and we need to find the following angles. So this is a bisector, so those are both congruent. And so if this is 68 here, we're also going to put a 68 there. So ADC is 68 and 68, which is 136. ABD, which is over here, we need to find. Now this is just a right triangle, so we could do 68 plus 90 minus 180. So 68 plus 90 gives us 158. 180 minus 158 gives us 22 degrees. Next we have CBD, which is the same angle, also 22 degrees. And last, angle ABC, which is the 22 and 22, so that would be 44 degrees. For K, we have the incenter here, and we need to find KI. So what we said about the incenter, it was equidistant to the sides. So from that, I can look at the values I have, and I know these values are all equal. So that would be KH is equal to KI is equal to KG. Now, two of them I know. I know KH and KG. I need to find KI. So I could set them both equal to each other, solve for x, substitute back in, and I would have the values. So KH is 7x minus 31, and that's equal to KG, 3x plus 17. I'm going to subtract 3x over, and I get 4x minus 31 equals 17. Adding the 31 over, I get 4x equals 48, and x equals 12. By substituting that back in, it doesn't matter which one we do. We'll do into kg. So we get 3 times 12 plus 17, or 36 plus 17, which gives us 53. Now if that's this segment, it's going to be all the segments, so ki equals 53 units. All right, on to our last one. We have S is the incenter. S is the incenter of our triangle. We have some different angles to work with here, and we need to find each of the angle measure. Now if we notice, PRQ, RPQ, and PQR are all the angles that make up the big triangle. So I know that the measure of angle PRQ plus the measure of angle RPQ plus the measure of PQR equals 180. I'm going to start there to solve, get my values of x, and start to substitute in. So we got 8x minus 10 plus 4x minus 14 plus 7x minus 5 equals 180. This gives me 19x minus 29 equals 180, which becomes 19x equals 209, and we get to an answer of x equals 11. So from that, I can substitute back into each of the angles and find them. So the measure of angle PRQ is 8 times 11 minus 10, which is 88 minus 10, or 78. The measure of angle RPQ is 4 times 11 minus 14, or 44 minus 14, which is 30. And the measure of angle PQR is 7 times 11 minus 5, which is 77 minus 5, or 72. A quick check, we see that 78 plus 30 plus 72 is 180. So we're off to a good start there, and I'm going to copy over my values here that I found. So we have those. I'm not going to write them inside. I'm going to write them here on the outside to see what we need. Now, if we look next, we notice that RPS, PQS, and PRS are all using parts of the angle bisector. So I'm going to split these in half and go 39 and 39, 15 and 15, 36 and 36. So RPS is 15 degrees, PQS is 36 degrees, PRS is 39 degrees, and then the last one we need is PSR, which is this angle right here. Well, I know it's a part of the triangle with 15 and 39. So I'm going to do 15 plus 39 plus the measure of angle, I'm just going to write S here, equals 180. So 15 plus 39 gives me 54. Should write this PSR here, PSR. We subtract it from 180. We get the measure of angle PSR is 126.